and welcome again to the Theories of Everything program. I'm David Tao. Viewers, it's not often in contemporary times that philosophy and mathematics talk to each other. And yet they should, because they're a natural fit. They've been together, they've developed together under the umbrella of natural philosophy since the beginning of our great civilization. But somewhere along the line, those two great disciplines diverged. Philosophy, in a sense, took the easier path in relation to mathematics. It focused on simpler number systems, simpler geometries that we now know do not reflect the real world of cosmology, of biology, of environmental science, ecology. These complex realities are reflected in the new, or supported by the new applied mathematics, as well as pure mathematicians, who've combined to keep the impetus going. But philosophy has stayed behind. But it's essential now in the 21st century, with the rate of knowledge growth, it's essential that these two great disciplines who've largely talked past each other for the past 2,000 years are reunited. And we're talking with someone on this show who is actively catalysing this dialogue, who's intent on this reintegration. And here's Dr. Jim Franklin, a philosopher of note in this country, but also an associate professor of mathematics at the University of New South Wales. He has established recently the Sydney School of the Philosophy of Mathematics to do just that, to bring these two great disciplines together so that both can equally support the huge impetus of knowledge discovery in the 21st century. Welcome to the show, Jim, and congratulations on the new school. The new school is the Sydney School of...
Called Sydney School in the Philosophy of Mathematics.
Okay, so that, I think your central aim here, and correct me if I'm wrong, is to look at the complexity of the real world more in terms of mathematics and philosophy, to, if you like, sidestep the older models, the Platonist models, in a sense, and go straight into the more complex realities of Aristotelian.
That's right, yes. We hope to have a philosophy of mathematics based directly on applied mathematics, yes, rather than like Plato and the formalist schools and other things that have been very big in the past, yes, going via pure mathematics. As if...
Well, that's right, and that's where the evolution had to start from, I guess, with the simpler
yes,
forms.
That's right. Applied mathematics came first and pure came later. So surely that's an indication that to understand what mathematics is really about, you should do the applied aspects first. And
yes,
think about,
of course, yes.
What is mathematics studying? And we say yes, symmetry, continuity, complexity, that was we talked about before. These things are properties of the actual real world, and we hope mathematics is going to grip them directly.
And also there's a rapprochement, I think, perhaps your word, of perhaps bringing philosophy and mathematics together to see a similar view of the world, perhaps. Philosophers have tended to gloss over complexity to some extent.
Yes, that's right. Philosophers have tended to hate complexity and think that philosophy should be about simple things, which is...
try to reduce complexity down.
That's right. So that's one reason why they haven't talked very well to mathematicians. I mean, philosophy and mathematics are the two great abstract disciplines that have been around for 2,000 years, but yes, for all the talk of each other, they have really talked past each other far too much.
Yes, well, at this time, I mean, there's a whole lot of reintegration of knowledge now, a more holistic approach to knowledge.
That's right.
To science.
Right. Yes, the disciplines are coming together, or at least they talk about coming together
to solve the hard problems.
That's right, to solve the hard problems, because there has to be multidisciplinary approaches to problems like ecological complexity, for example,
of course,
predicting how the ecosystem is going to develop. All the disciplines, mathematics, physics, philosophy, ethics, need to get together.
To solve the hard problems.
That's right. That's right. They're too hard to solve by any one discipline.
Yes. Well, of course, mathematics has always been, I mean, for the last 50, 100 years, quite effective at solving real-world problems in the areas of operations research, production planning,
timetabling and so on. It's done a great job. Perhaps economics is not one of its more notable successes, but in many ways it has, and it's been expanding the areas that it's been moving in. But there are still areas where it's not successful and needs to make a greater effort. Weather prediction has been a famous long-term effort, and it's slowly getting there, but as everybody knows, there's much further research needed.
Yeah, that's right. Well, they are, weather systems are an example of perhaps chaotic systems in a sense.
There's a potential for chaos in those, yes.
And turbulence and so forth.
That's right. And for example, in global warming,
yes.
Part of the problem is how to make the most of the data of the paleoclimate. Very difficult problem to understand what is the natural variability of the complex climate system.
As against the man-made
that's right, to
addition.
sort it out from the man-made additions.
Yes.
Very difficult, but it's a matter of melding complex models with data sets, often data sets much smaller than you would wish.
Well, that's right. I mean, that comes into a broad area perhaps of signal processing,
that's right.
analysis,
Yeah,
etc.
That's right. Those are old disciplines that need to be put together to get the big picture.
Yes. Well, there is some fascinating stuff occurring, of course, and it has been for 100 years. Also, to understand the quantum nature of reality, and going quite deep into, and that's where actually mathematics has been absolutely, obviously essential, because at that level our experience stops. Even the most powerful microscopes tend to be limited.
So the mathematics has been successful, and interpretations of it philosophically have not been so convincing, possibly.
So the philosophical understandings or interpretation of tools such as vectors and tensors and manifolds and so forth, and operators in general, matrix operator, has lagged the mathematics?
That's right, yes, yeah. That's right. And part of the problem we believe is that people have been not so prepared to see those operators and so forth as really telling you directly about the real world. My colleague in the Sydney School, Adrian Heathcote,
yes,
is especially interested in interpretations of quantum mechanics, and he says Hilbert spaces, as talked about in the formalism of quantum mechanics, they're out there. Yeah. Hilbert spaces are real. There are really Hilbert spaces out there in the quantum world.
Yeah, with infinite dimensional
yes,
spaces.
Sure.
Sure. So infinity is not just a concept, is it?
No, reality can have its infinite number of dimensions.
Yes. Well, actually, there's some, as you probably know, there's been some interesting work lately with concepts of the multiverse. Well, not concepts, but actually the physics of the multiverse, and looking at an infinite number of universes too. So perhaps Cantor wasn't so far off the mark there. But yes, that's his model was a bit simplistic for the latest multiverse models.
Still, we have to apply. Cantor showed that you could have enormous numbers of worlds of enormous sizes, enormous and different infinite sizes.
Yes.
Well, whether our real world actually instantiates that is hard to say, but it gives us a way to think about it, and a way to think about it realistically.
Well, coming back then, all right, I mean, it's very hard to have a conversation on philosophy and mathematics without mentioning Einstein. And Einstein was a little more sceptical of mathematics, I think, in his famous quote, and I think you've mentioned it, that so far as the properties of mathematics refer to reality, they can't be certain. He's saying, and as far as they're certain, they don't refer to reality. Is he saying there, what's he saying? Is he saying that mathematics can't model reality, basically?
Yes, he's saying he can't model it accurately, at least, and that he's taking essentially a Platonist view that we don't agree with, saying that there's a gap between model and reality. And we say that there doesn't have to be. I mean, sometimes models are, of course, too simpler than reality, but they don't have to be. An example we like a lot is the one of Euler in the 18th century, who proved that the citizens of Königsberg couldn't walk around the bridges of Königsberg. There are seven bridges in a certain arrangement in the islands. Yes. And he said, Euler said that the citizens were right to believe that you couldn't walk around the bridges without walking over one of them twice. Now, there was no simplification or model or gap there. That was something he proved mathematically about the bridges themselves. So that example is a counterexample to Einstein's statement. Sure, there can be mathematical necessity directly about reality.
Right, and as you say, I mean, the whole area of getting closer to reality with these abstract concepts is happening with algebraic topology, for example. manifolds, and understand and bringing in areas such as knot theory.
That's right, and knots are a good example. Knot theory is, of course, very high-powered algebra, but
Yes.
knots are real things, and the knot theory tells you about actual pieces of string and how they can knot.
Well, biological processes
Yes,
such as DNA.
DNA is the same, applies just as directly to them because they share the same linear structure that curls around itself.
Penrose has had some interesting things to say, of course, also. I don't know whether Penrose is a Platonist or an Aristotelian.
Not sure of his views, no.
He seems to be a bit of a wild card, but he's an amazing person. Of course, he brought up the pentagon tiling model as well, saying that that couldn't be done in reality solely with pentagon tiles. You couldn't tile a floor without making some adjustments. But he did bring up an interesting point. I mean, and Einstein perhaps may have been alluding to this, that there are some mathematical truths that aren't reflected in reality. Is the reality, if you like, is reality a subset of mathematical reality? Is the real reality a subset?
Yes, well, it is, but if a mathematical reality, if there is a consistent mathematical reality, then at least it could be in physical reality. So
It is a possibility.
It's a possibility, that's
Yes.
right. And a lot of it is an actuality. Of course, it's true that there are some numbers too big for the universe to fit, so if there's only so many fundamental particles. So in that sense, mathematics goes beyond physical reality, but only just a little bit beyond.
That's not the multiverse, though.
That's not yeah, that's right. If that's true, then perhaps, if the multiverse theory is true, perhaps all mathematical models are instantiated somewhere.
Somewhere, yes.
Somewhere.
Well, that's Tegmark's theory. Tegmark says that within different mathematical systems, there is always a universe that can be modelled on a particular mathematical system. But again, that's another area that we don't have to get into. But he did raise, I don't know whether it was Penrose, but everyone raises, of course, in this context, fractals. Now, fractals were interesting to me, apart from their incredible beauty, etc., because no one had actually visualised or seen the results of fractal mathematics until how long ago, when they sort of...
Really only the 70s, when they had the computer graphics to show you what was really in there.
So certain ideas, certain propositions are that the equation that would generate the Mandelbrot set, for example, including I think z squared plus c complex numbers, had the potential to realise those shapes and patterns, but that potential had never been realised. So is this a bit like mathematics?
That's right. The purely mathematical work will show you what potential there is to be realised. You've got to get out in the web and see what potential is realised.
Yes.
But the mathematics can certainly tell you about what is possible.
About what is possible and what perhaps is not. So it can, it can.
Yes, that's right. It rules certain things out.
But those the things that it doesn't rule out may not be at this point in time in reality.
May not actually. Yes, that's right. But that's not philosophically different to saying that there is a large number of shades of blue, and it could be that one of them is not instantiated in the actual world.
Of course.
We can be fairly relaxed about that. The science of blue is about all shades of blue, whether instantiated or not.
Well, that's
the same with number theory.
Well, the Inuits have about 8 different words for white, 8 different descriptions of the colour white, so that's a good example where they have instantiated it up to a point, but that could go for anything, yes. That could apply to anything, but that was a real world situation. Of course, as the ice melts, perhaps they won't have the need, then that reality will change, perhaps. That brings us to, I mean, I'm particularly interested, as I was skimming over some of the papers that you've written, etc., the central postulate that mathematics can closely reflect complex reality. In fact, it revels in complexity. Applied mathematics can revel, and the school will be doing that. But it came to the broader question, as I saw it, as to whether mathematical objects or models can be classed as real things. A bit like the fractal situation. It's a mathematical model in a sense, but it sort of it realises itself in these incredible patterns, which are actually in reality because of clouds, trees, shapes, etc., etc.
Yes.
But the model itself, is there a debate in philosophy over whether the models are actually the groups and the network models, for example, reflect reality?
Yes, well, the Aristotelian view is that they do reflect reality. Perhaps we wouldn't call them things, we call them properties, like blue. So our view is that a network model is a property of real things the same way as blue is a property of real things. It can affect you. A network, to say that the Sydney train network has certain patterns in it, for example, circuits, affects how you can travel on the trains, just as things having a certain colour affects how you can see it. Yes, it's actual. The network structure is actually out there in the thing.
Well, if we come to a mathematician, physicist like Edward Fredkin, who actually says, I think we've discussed on a previous show, Wolfram's book, Stephen Wolfram's book on cellular automata, which does provide an alternative model, the differential equation to model very well, but Fredkin says that the model is it. The cellular automata models can be used to represent momentum and forces and particles and so forth. So he's sort of trying to bring together the model with the reality.
Yeah.
Is that something that your school will be?
Yes, we'll certainly approve of that. Of course, it's not for us to do the physics and decide whether the reality is correctly modelled by a cellular automata or better by a partial differential equation. But no, that's right. But the business of mathematicians is to provide the possible models and see which ones are actually structured the way that reality is.
Well, this would come back to space-time as well, where there are now quantum gravity models that suggest that space-time is actually made up, underneath the sort of material things, the quarks and the electrons, made up of information flows through networks. And that comes to this whole issue of information. Is that and bits and quantum information and everything else, but how do you see information fitting in between a mathematical object, or Shannon's view of information, whatever, and the real world, which some physicists are suggesting is it?
I think the information has to be realised in something, some physical reality, though what the nature of that is hard to say. It could be curved space-time or something. But information certainly, to speak of in information theoretic terms, certainly emphasises the patterns in reality, because the information is a measure of the complexity that is in there at the lowest level.
Yes.
So we certainly approve of that, but perhaps we prefer you to look at the patterns that are actually realised in the flow of bits. We think of the bits as material and the patterns and structure as what's in that material.
Do you think of the mathematics as the mathematical model as the bits? In other words,
we prefer the patterns in the bits. I mean, the point of bits themselves are not information. It's what you can get out of them.
Sure.
So
but where's the maths? The maths is the structure of the bit.
Well, yes, that's right. So, for example, the maths would talk about repetitions in the bits, for example, that mean something. So when you're transmitting, that's right. So when you're transmitting, say, video in image, it's important that there's blocks that are homogeneous, that tell you that there's a flat background or something. And it's that kind of pattern that mathematics is going to find in the information.
Yes, well, of course,
it makes it mean something.
Pattern recognition is
huge. That's right. Pattern recognition is perhaps one of the central things we see as mathematical reality and mathematical epistemology. So we hope to connect. We haven't talked much so far about how you know mathematics, which is a traditional, almost half of philosophy of mathematics. But we hope to connect it with the pattern recognition capabilities of the visual system, for example.
Through computing models.
Yeah, that's right. Computing models. So, and through baby experiments, for example. There's marvellous baby experiments that video babies as soon as they're born and see what sense they're making of the flow of information into them.
Well, I have to push this point a little further, actually, because as an outsider, but as someone who's interested in the general flow of ideas, if you like, and there's another concept of ideas in consciousness, of course, whether that is an outcome of a mathematical, whether that's a mathematical reality embedded in consciousness and how that relates to actual reality, etc.
That's right. Yeah, a very good question. I think that's a cutting-edge area, what the structure of consciousness is and what connection it has to what consciousness knows. There's work being done by Federation Fellow David Chalmers at ANU.
Right, yes.
He hopes to understand what consciousness is like, not its causes and effects and everything, just what it is like in itself. And mathematics is one of the few things you've got to work on.
Well, that's right, and it could be a bridge.
And that's right. And what connection has it? So, one of the structures of consciousness that's most prominent is that it has a kind of centre and surround structure. So there's something you're concentrating on, but you're not totally unaware of the things that are surrounding it. Things you've remembered in the past. Things are at the corner of your eye.
Yes.
Now that's very important somehow for what consciousness does, how it knows things.
It is a central problem in knowledge understanding.
That's right.
But it also, there's a wider area that I want to just touch on briefly. Again, it relates to cellular automata and so forth. It's virtual reality. There's a realisation of modelling and information that actually is starting to impinge on our world, our real world, if you like, quite a bit. People spend a lot of time in cyberspace these days. And really, when it comes down to seeing the photons flowing in from outside that window, created in my brain, as we talked about, as consciousness, it's just bits of information, photons, etc., coming in and impacting.
It's extraordinary how active your brain and mind is to make a structure out of that simple flow of bits.
Yes, that's right. So if I had a virtual reality picture that modelled that, I wouldn't know the difference.
No, that's right. So you'd be giving you the same flow of photons and you'd be performing the same algorithms on it and constructing a virtual world inside.
So the algorithms actually become more major in a virtual reality. If you
it calls attention to how major they are, but of course they're major in the real world as well. You don't
have relationships in the real world without.
That's right. You have to work hard to construct your vision of the real world, but for it to work, it has to be that the structure you get out of that flow is something like the structure of what's out there. You have to know where the rigid edges of the world are, so you plan a route around the door.
Yes, of course.
That's right, and you have to get that structure in your consciousness out of something that's not the door, but just a flow of bits. Truly extraordinary.
Right. Well, that's we'll leave that there. I think we've sort of pushed the boundaries. But the point of the school, of course, is that we'll raise these questions.
Yes.
And we'll look at them more closely. That's
right. And we'll hope to remove some of the junk that has prevented us seeing the direct structure in the world. Platonist junk, formalist junk.
Yes. Do you think philosophers have had a bit of an easy ride, in a sense, by focusing purely on this more simplistic?
That's right, yes.
Numbers and sets.
That's right. Philosophers have said, look, if we just understand what numbers are, then we'll know all about mathematics. Now, that's quite untrue. You should start with meteorological modelling or the theory of symmetry and continuity in complex systems.
Yes.
And sorting out about numbers doesn't necessarily help with that at all.
No.
And I think focuses attention onto a more Platonist field that is not good.
Is this a global problem with philosophy at the moment? Or are the sort of...
Yes, it is global, but we like to think that in Sydney we're rather more realist than anywhere else, and that we have something to tell the world.
Yes, that's
realism about mathematics and realism about ethics, for that matter. I've certainly written on the parallel between mathematics and morals, by which I meant that ethical truth should be seen as just as real and in the real world as mathematical truth.
Absolutely.
And again, I think Platonist and idealist and nominalist and other errors have prevented us seeing the truth in both of those areas.
Well, look, Jim, I'm very much appreciative. I know that, again, this is an introduction only to the processes and names of the school, but being on the cutting edge must be very exciting for you and the members.
Definitely.
Even in your virtual school.
Yes, that's right, yes. The school doesn't have a location like the numbers itself. It doesn't.
So the ideas flow, but through some
that's right. That's right. Flow through our website.
Thanks very much again.
Thank you.
Thank you, Jim. I'm David Tao, and you've been watching the Theories of Everything program again. I'll look forward to seeing you again next week.